We shall now calculate force due to liquid pressure on a vertical wall. Now, here is a vertical wall. This one, this left part is a vertical wall, and here on this side you have a liquid, and the height of the liquid happens to be h, and b is the width of the wall. So in the this three-dimensional diagram, so there's a wall, and there you have the liquid here, there, and there. Like this you have the liquid surface. Thus. And as you see that width of the wall is given as b, so that width b, and the height of the liquid layer is given to be h. So here we have to find the force exerted due to liquid pressure. We will not count the atmospheric pressure here. Force due to liquid pressure on the vertical wall. So for calculating that, and this height is obviously h. So for calculating that, we will consider a height y below the free surface of liquid. So this is the free surface, right? And the top surface of the liquid is the free surface. Okay. So there you take a small rectangular strip. So the thickness is dy and the width is b. So the area of the rectangular strip is suppose dA. So that dA is equal to b times dy. And now let's calculate the forces on it. So the force should be pressure multiplied by dA. So there it is. That's it, right? So this force is dF actually. So dF is the force on the area dA. So that what is dF equal to? See, dF is equal to rho gy, pressure, times dA. So what is the net force F? So the net force on the wall F, so F will be equal to integral of dF, right? So the net force on the wall is F, right? On the wall due to liquid pressure, solely due to liquid pressure, is F is equal to integral of dF. So integral of dF means integral rho gy. So dA will substitute b dy. So the integration limits will be from 0 to h. So F is equal to rho gb integral y dy. So that will be h square by 2. So that is rho g h divided by 2 multiplied by bh. So this is for the general formula. So it will be pressure at centroid into the area. I mean, area means the weighted area of the wall. The surface of the wall which is in contact with the liquid, that is known as the weighted area. So this is a general formula I have written: pressure at the centroid into area. What is centroid of the weighted area, right? By centroid I mean the centroid of the weighted area. So here it is a rectangle, right? Here the weighted area is a rectangle of height h and width b. So the centroid of the rectangle means it is this. So it is the center of mass of a lamina. Lamina having the shape of the rectangle. That is the meaning of centroid of area. So this is the general formula. So F equal to pressure at centroid multiplied by the area, that is the weighted area. Now the weighted area may not be rectangular. Then we will do that general proof now, where the weighted area is not a rectangle. So I'll take any arbitrary shape of this weighted area. I think you can guess what it is all about. So this is a liquid. That means if you look at a vessel, so vessel has a shape like this. So that's the liquid surface on top. So the weighted area is this one. It's not a rectangle, so it is shown here, weighted area. So here also the way of calculating is same. Suppose the height is h and here you take y here and dy here. Here the width is not constant, the width varies. So I'll keep this area as dA only. Will not write it as in terms of the width because the width is not constant. So here it is, this is a force dF acting on this area dA. So that's dF, right? So what is dF? Sorry, I write like this. So that's dF, right? So what is dF? Rho gy multiplied by dA. So in the front view, the figure to the left shows the front view. Here the force vectors will look like dot. So the force vectors are coming out of the plane of the board. So that's dF for you, coming into us. So what's the total force? So the net force is equal, net force F is equal to integration of rho gy dA. So we can write rho g, so integral y dA, right? Now so that's equal to rho g integral y dA divided by A and again multiplied by A. So integral y dA by A is actually integral y dA divided by A is yc. C for centroid. So that's y coordinate of the centroid. Centroid of the weighted area. So there, this is the general proof for this situation. That is, so let's write this. So this is rho g yc times A. So rho g yc means that is pressure at centroid multiplied by A. A is the area, that means the weighted area. So thus we have found out the force on a vertical surface in general the shape of the surface may be rectangle, may not be a rectangle also. Now we have calculated the force part. Now we'll find out the line of action of the force. So any distributed force has got a line of action. So this is a wall and this is a liquid surface. So the force due to liquid pressure varies in the following way. As we go down, the force increases on a certain section because pressure increases due to height. So we have to find out the line of action of the distance of the line of action of the force. By distance of the line of action of the force, we mean that so instead of having this distributed force, we will replace it by one force, that is the net force F. These are all dFs. So here it is, the force varies with y in this following way. Now here we replace this by the net force F, and the net force should be at a certain distance. So let the distance be y bar. So this is the line of action. This thing is the line of action of the force. Okay, now we have to find out the line of action. The whole concept of this line of action, whether it be this hydrostatic force or whether it be weight or any distributed force, the concept is that from a certain point, say this point O here and this point O here, the torque due to distributed force, the torque due to, or rather I should put it up like this, torque of the distributed force for the left figure is equal to torque of net force at a distance y bar. So that is how we define the line of action and the distance of the line of action from the point O. So here so at a distance y, the force happens to be dF, and we already know, so the torque is y multiplied by dF. Now so in the right hand side it will be F multiplied by y bar, right? So integral y dF from 0 to h. So now we will expand this. So integral from 0 to h, y multiplied by dF. dF is how much? Rho g y into b dy is equal to, what is the net force? Net force is rho g h by 2 multiplied by bh, right? So into y bar. Now we have to calculate this y bar in the following way. So rho g b, so integral y squared dy, right? So that's y cube by 3. So this will be h cube by 3 is equal to rho g h square b by 2 times y bar, implies this y bar is equal to 2h by 3. That means the distance of the line of action of the hydrostatic force on the wall is at distance 2h by 3 from the free surface, or you can say it is h by 3 from the bottom. Here we will learn how to find out force due to liquid pressure on a curved surface. So here we will use a very special technique without integration. Normally if one sees any problem like this or problem of this sort, what comes to mind first is there is a curved surface, you know pressure, calculate force, then integrate to find out the net force on the curved surface. But we won't use any integration, right? Now suppose there is a curved surface. Now the curved surface is drawn. I'll explain what it is actually. So this is a quarter cylindrical shell. Quarter cylindrical shell of radius r and say length L. That means in the 3D diagram it will be of this sort. This type of a quarter cylindrical shell, right? This is just this is an extension to show you that where the axis of the cylinder is. This one, this is the axis of the cylinder. In this diagram this axis is just like a dot. Okay, now this length is given as L and this radius is given as R. So you have to find the force due to liquid pressure on the curved surface. So liquid pressure applies here, right? Liquid pressure is applicable here. So usually what people will like to do is consider a small area dA and calculate the height and the force, calculate the force and integrate. We told you before that we will not do any such thing. Rather what we will do, we will choose a free body diagram, an appropriate free body diagram to calculate the force. Now here the free body diagram that we will choose is the following. See, I am coloring the free body diagram. We will choose. So this is it. This is the required free body diagram. Now let's draw. We can draw this separately, right? Just here. So what I have drawn here is the free body diagram of a certain portion of the liquid itself, right? We have not included the curved surface, that's the liquid itself. Now, so the force due to liquid pressure on the top surface, how much it is? Force due to liquid pressure on the top surface. Say this be F1. F1 is force due to liquid pressure on the top surface. So it's actually the weight of the liquid on top of it, right? Or you can just write pressure into area. So what will be the height? Obviously the height is H minus R. So you can write this. The force F1 on the top surface is rho G into H minus R multiplied by R into H, right? So again, if I draw the figure, draw the 3D one, 3D figure here. The force on the top surface is F1 and the force on this surface is F2, that is the vertical surface. So in this diagram, in the 3D diagram, this F2 is this force F2, right? What is F2 equal to? So you know F2 is equal to, see, just now we have solved these all problems, right? force on a vertical surface is pressure at the centroid. So that's a rectangular surface. Pressure at the centroid means from the top, the height is how much? H minus R by 2, right? H minus R by 2. So F2 is rho G, because the total height is H. So this is midpoint, so R by 2 from the bottom. So that is why the centroid of the rectangular surface, centroid of this rectangular surface is the midpoint. Okay. So rho G H minus R by 2, that is pressure at centroid multiplied by the area itself. So what is the area? So that's in the diagram below, you will see this is R and that's L. So area of the rectangular surface is R multiplied by L. So that is how we got F2 also. And next also W is weight of the considered volume of liquid. So what is W equal to? W, how much is the volume? You have to calculate the volume. For the full circle, it would be pi r square, or the area of the face of the quarter circle is pi r square by 4, and multiply it by L, you get the volume multiplied by density mass multiplied by G weight. Okay. So now we can calculate the force exerted by the curved surface on the curved surface of the liquid in contact with it. So that's Fx and say Fy. Fx and Fy. So we can write let Fx and Fy be force on the curved surface of liquid by the quarter shell, right? Or due to the normal force between the quarter shell and the curved surface of the liquid. Be the force components, right? Be the force components. Now we have chosen our free body diagram of the liquid. Now that part of the liquid is at rest, so we can write Fy is equal to F1 plus W. F1 and W we have calculated, and Fx is equal to F2. So the net force is root over Fx squared plus Fy squared. So this curved surface of the liquid, the curved surface of the quarter shell rather, will experience a force due to the liquid pressure from the top, obviously, because liquid will exert pressure from the bottom also. So that's Fx here and Fy down. See, that's Newton's third law. So due to this Fy, it's action reaction pair, and due to this Fx on the top, the action reaction pair. This is how they are related, Fy and Fx, and here Fy and Fx. Say in this problem, we have to find out the force due to liquid pressure on the curved surface of the hemisphere. So again, many students will think in that way. Okay, we have a curved surface, let's calculate the pressure at some point and take a small area dA and then integrate, but that's not required at all. So to find the force due to pressure on curved surface, you know that pressure on the curved surface acts this way, normal to the surface in contact. But the force due to the curved surface, if you see it properly, so the force is solely due to the weight of the liquid residing on top of it. The weight of the liquid residing on top of the curved surface. Now on top of the curved surface, the liquid which resides is the following. This one. So the weight of this shaded liquid, which I have just shaded with blue, the weight of that liquid, weight of this liquid, shaded part of the liquid, is equal to force on the curved surface. So we can write force on the curved surface is equal to weight of this shaded part of the liquid. So how much is the volume? So volume is either radius is r, so its volume is pi r square h, and subtract from it the volume of the hemisphere, 2/3 pi r cube. So that's volume into rho, mass into g. So rho is density of the liquid. So that's the force on the curved surface. The net force on the curved surface will be in downward direction, F1. So we can also verify it whether it is true or not from the concept of buoyancy. So suppose this hemisphere, so liquid will get from bottom, get into the small space, and from bottom it will exert a force F2, which is equal to pressure rho g h, the whole height, multiplied by pi r square. So that's F1 due to this whole force on the curved surface. So you can verify whether F2 minus F1 is weight of the displaced part of the liquid. That means if so instead of having this hemisphere, if there were liquid in this region, what would have been the weight? So we are using basically Archimedes principle. So that's V rho g. Rho is density of liquid and V is 2/3 pi r cube rho g. So from this viewpoint also it matches that. So we know this F2 and we know V rho g. So by subtracting also you can find F1.